this is the one of the best simulations ever produced on a black hole. But the problem with these simulations is that they highly depend. The problem with highly dependent on general relativity is that we get the results what we actually predict. What if general relativity is wrong about black holes? We won't get the actual results what we want. So, the real image of a black hole, and it was done at 2019. So EST and black holes. EST stands for Event Horizon Telescope, and it is the name of the telescope that we used to image the black hole. When it comes to imaging a black hole, it's a very complicated process, and as black holes are very hard to detect, we need very high cutting edge technology to detect them. So before going into how we managed to capture the first image of a black hole, let's just go black hole. So what are black holes? Black holes are special regions of space-time where gravity is so strong that even light can escape. The velocity of a black hole is greater than the speed of light. In short, as nothing can go faster than the speed of light, in short, nothing which crosses an event horizon can come out of a black hole. Black holes are commonly formed as a result of supernovae collapse of giant stars under its own gravity, and they ranges from a few solar masses to even billions of solar masses. As they doesn't emit any kind of electromagnetic radiation, they are picture black to us, and it's impossible to know what's happening inside a black hole. Called singularity hidden from us inside a black hole, and understanding it is crucial to understand the evolution of galaxies, supermassive black holes, galaxies, and also our own existence. So mainly there are three types of black holes classified based on their masses. Stellar massive ones are the smaller ones, which has a mass ranging from 4 solar masses to less than 100 solar masses. And when it comes to its origin, they are formed as a result of supernovae. And when it comes to intermediate black holes, its mass ranges from hundreds to even thousands of solar masses. Their formation is, their origin is as they merge with other stellar massive black holes. When two stellar massive black holes merge together, intermediate black holes are formed. When it comes to supermassive black holes, they are the gigantic monsters present at the center of galaxies. Origin of supermassive black holes are still unclear to the scientific world and is a hot debate among the astrophysicists and cosmologists. Their mass ranges from millions of solar masses to even billions of solar masses. So, imaging a black hole. We have seen that supermassive black holes are very gigantic. To detect. And even the title given here is a bit misleading, that black hole holes kind of cannot be directly imaged. We actually which orbits or kind of orbits or around some of the black holes. And see the dark region at the center of this accretion disk. And we call it as the shadow of the black hole. Image it. And from this image, we can see the surface, so-called event horizon, and inside it, hidden from all of it surrounding, is the singularity. And how we manage to image such weird objects in space. Even though supermassive black holes are gigantic in sizes, the nearest one to us, to Earth, is 27,000 light years away from us. This makes them really small for our cameras, for our telescopes to detect. So when we put some numbers into a calculation to understand object in night sky, it says that we need a telescope at an aperture around the size of Earth to image such our supermassive black holes. And clearly, it is impossible for us to make such a telescope using our current technology and resources. So what we actually do here is make a global network of telescopes all around the globe. They are actually radio telescopes, and by combining the data collected from it, we can filter out and sort out the data and create images of a black hole. So EST stands for Event Horizon Telescope. The EST project combines data from several very long base interferometry stations.
Okay.
also there is a futuristic idea which with our current technology might not be possible, but in very near future itself it might be possible to make a array of space telescopes around the sun or in the Lagrange points of multiple planets to make a very large collaboration or very large space array of telescopes, giving us a very wide aperture of the telescope, of the virtual telescope, to image a black hole. Understanding supermassive black holes is crucial in understanding the evolution of galaxies in our early universe. So imaging them is very crucial. Understanding supermassive black holes and gravitational waves, etc., can give us key to understanding the relation between quantum mechanics and general relativity. As said earlier, there is a gap between, in the previous sections, it is said that there is a gap between these quantum mechanics and Einsteinian relativity. So, to rectify these gaps, singularity may play a crucial role. So, understanding singularity, understanding black hole is very crucial in our further development in science. Thank you.
Thank you, Anne Joseph. Thank you for a wonderful presentation. So, we would like to know the comments of our judges about Anne Joseph's presentation. So, I would like to move on to Dr. C.B. Katta for his valuable comments on Anne Joseph's presentation. Sir, sir.
Overall, it was a very good presentation. I must admit that my knowledge about black hole and the subject is not very extensive. Only a layman's understanding about that. I would say that your slides were very good. And the presentation style as well was excellent. And I would say the content, you have covered the points, whatever you wanted to say, and it's well appreciated. The techniques which you have explained, of course, its limitations as well as what it can do and what more is required has been well thought out. So at least I would say that I have been educated on that part of it. I appreciate that. And your communication skill is very, very, very good. And overall, I would rate it as very high. The presentation.
And Joseph, yeah, as Mr. Katta said, overall, very good presentation.
Thank you, sir.
The slides were good. But, if I look at the critical eye, I should give you some feedback also, isn't it?
Yes.
So the very first slide, there was a figure. And there was some text written under that, which is not readable.
So the first
Very
image.
first slide.
Very first image.
Not the title slide, the other one.
Oh, okay, sir.
Huh?
Oh, okay, sir.
Okay. So you should always be careful, So readability. I mean, that is, I'm just telling you just for you to make sure that you don't make such.
Okay.
Okay. And then I was very closely observing you. Your focus was onto the PC.
Yeah.
Okay. And looking only at the panel judges here, not probably looking at the audience totally. Okay. These are finer aspects. Otherwise, excellent. Okay. Good. Right.
It was a nice presentation. Content-wise also it was very nice. I just want to ask you one question. Have you heard about Hawking radiation?
Yes, ma'am. Yes.
So black holes, are they really black?
They are quite black, but when it comes to electromagnetic, I'm actually saying about picturing a black hole. So actually, Hawking radiation states that it doesn't mean an object is crossing a black hole's boundary. Actually, when according to quantum fluctuations, a particle can come into existence at any point in time of space or time. So when it comes too close to event horizon, particle comes out as two parts, right? Matter and antimatter. So when it comes out like as a particle, antimatter and matter, when they quickly annihilate each other in usual cases, but when it comes to too close to event horizon, one part may get into the black hole and one part may get out of the black hole. So it's kind of not a way of saying it just cross out of event horizon, but actually we have no direct evidence of Hawking radiation, and also we can't use it to image a black hole. So
I just wanted to know how much your excellence on black holes. That was nice, and thank you. And you have heard Thomas's comments about the final aspects of presentation. That would really help you to improve further. So thank you and all the best.
okay, thank you.
One more point. And there is given a time limit.
Yes, ma'am.
Next we have Aditya here.
Good evening, respected scientists and fellow students. My name is Abdeva and this is my presentation on rocket fuels and their advantages and disadvantages. Common bipropellant liquid fuels. RP1 dash LOX. RP1 and LOX are one of the RP1 and LOX are one of the most common bipropellant fuels out there, and it is used on several rockets such as SpaceX's Falcon family, the Atlas rockets, Saturn V, Electron, Neutron, etc. etc. It's a carbon-based fuel, it's a carbon-based fuel and it's a highly refined version of kerosene. Its advantages are it's cheaper than most fuels, it's stable at room temperature, so it has a low explosion risk, and it's more energy dense than liquid hydrogen. The disadvantages are it has less ISP when compared to LH2. It exhausts components of multiple pollutants, and it leaves soot in the engines, which is bad for use. Liquid hydrogen and liquid oxygen. LH2 and LOX are another extremely common rocket fuel used on SLS, shuttle, Blue Origin's BE-3 engine on the second stage of the new plane, and the first stage of the new Shepard rocket, the upper stage of GSLV rockets, and the Delta IV family, Centaur upper stages, and the DC plus upper stage. It has the most ISP of any other rocket fuel on Earth, and its exhaust is mostly water vapor, so it's not polluting. It's very light and powerful and is cheap to manufacture. But some disadvantages are that it is very not dense and it's difficult to store because of the small size of the atoms. It needs larger tanks because of low density and needs a lot of insulation to prevent it from being boiled off. Hypergolic fuels, this one I am focusing on unsymmetrical dimethyl hydrazine and monomethyl hydrazine, both paired with nitrogen tetroxide. They are another type of common rocket fuel and they are mainly used on launch escape systems and most other rockets. They are used on the GSLV Mark II and Mark I. The Space Solar engine, the AJ-10 engine, and the Russian Proton rocket, and the second stage of the Ariane 5. It starts combustion immediately when it contacts the oxidizer, so it's suitable for launch escape systems. It can be very safely stored as liquids at room temperature and are very reliable. But some disadvantages are that they are very toxic, corrosive, hard to handle, and extremely carcinogenic. Liquid methane and LOX. Liquid methane and liquid oxygen are newer form of rocket fuel used on SpaceX's Starship rocket and Blue Origin's BE-4 engine will be used on ULA's Vulcan rocket and the New Glenn first stage. It's also hydrocarbon like Apple.